Imagine watching a car crash, but the impact takes 50 million years to happen. No sound, no motion visible to the eye, no sudden destruction. And yet, the energy released would dwarf every earthquake humanity has ever recorded. This is how continents collide. To us, the ground feels permanent, stable, ancient, immovable. Cities rise, civilizations fall, languages vanish, yet mountains stand unchanged across human history. Because to human perception, the planet barely moves, but Earth does not measure time the way we do. Beneath your feet right now, the ground is traveling very slowly, unstoppably. The surface of Earth is not one solid shell. It is broken, fractured into enormous slabs called asterisk tectonic plates, asterisk. These plates are not small fragments. They are continental-sized rafts of rock, some larger than entire oceans, floating on a deep layer of hot, deformable mantle rock. They drift at roughly the speed your fingernails grow, about 2 to 7 centimeters per year. Slow enough to ignore, fast enough to reshape the world. Every second that passes, the continents shift a tiny distance. Over a human lifetime, a city may move a few meters. Over recorded history, entire countries shift kilometers. Over millions of years, oceans open and close, and eventually continents meet. But continents do not behave like islands drifting on water. They behave like unstoppable masses of stone carrying unimaginable weight. A single tectonic plate can weigh more than every building humanity has ever constructed, combined, multiplied millions of times over. When one of these giants changes direction, nothing on the surface can resist it. Forests, rivers, coastlines, and ecosystems all become passengers. Yet a collision does not begin with impact. It begins with a journey. Two continents may start on opposite sides of a vast ocean. Between them lies thousands of kilometers of seafloor, volcanic ridges, deep trenches, and ecosystems living in darkness. For tens of millions of years they move toward one another without consequence. At first, the distance seems infinite, then measurable, then inevitable. Long before land touches land, the ocean between them starts dying. Because oceanic crust and continental crust are not the same thing. Oceanic crust is thin, dense, and heavy. Continental crust is thick, buoyant, and stubborn. When oceanic crust meets a continent, it sinks beneath it into the mantle, a process called subduction. This happens continuously around the world. Entire oceans are recycled back into Earth's interior over geologic time. But continents are different. They refuse to sink. So when two continents approach each other, the planet encounters a problem it cannot easily solve. For millions of years, the ocean floor between them disappears into the mantle. Volcanoes rise along the edges of the continents as molten rock escapes upward. Earthquakes rumble across deep trenches. The ocean narrows slowly, a shrinking scar across the planet. Marine species living there have no warning. Coral reefs vanish. Deep-sea plains fold. Ancient ecosystems collapse. An ocean that existed for hundreds of millions of years can be erased completely. By the time the continents arrive at the former seabed, the water is gone. Now nothing separates them, and still they move. There is no sudden impact like objects colliding in space. Instead, The first contact is subtle edges touching, sediments compressing, rock layers beginning to fold. For thousands of years, nothing dramatic appears at the surface. Rivers continue flowing, forests remain undisturbed, but underground pressure builds. Continents are thick, up to 70 kilometers deep. They cannot easily slide beneath each other because both are buoyant relative to the mantle. Neither wants to go down, so neither does. Instead, the crust begins to crumple. Picture pushing two carpets toward each other across a floor. They don't overlap neatly. They wrinkle, they stack, they fold upward. The same happens to rock, except rock behaves differently under immense pressure and temperature. Over millions of years it flows, bends, fractures, and fuses. The boundary between continents becomes a compression zone thousands of kilometers wide. The ground shortens horizontally but thickens vertically, and slowly mountains are born. But at this stage, mountains are not yet visible. First comes deformation, invisible but relentless. Rock layers that once lay flat under ancient seas tilt at impossible angles. Fossils buried at shallow depths are pushed kilometers downward, heated, transformed into metamorphic stone, and then lifted again. Nothing here is quick. Nothing here is temporary. From a human viewpoint, nothing is happening. From Earth's viewpoint, everything is happening. A city could exist at this boundary for 10,000 years and never notice the continent is being squeezed beneath it. Yet over geological time, that same location may rise several kilometers into the sky. Collision zones are places where the crust is continuously trying to occupy less horizontal space than it used to. But rock cannot simply disappear. It must go somewhere, so it rises. And as it rises, gravity resists it. Erosion attacks it. Rain, wind, and rivers grind down the forming highlands even while they grow. Mountain building is not a moment, it is a balance between uplift and destruction. The planet wrinkles while simultaneously sanding itself smooth. Deep underground, temperatures climb. Pressure transforms ordinary sediment into slate, then schist, then gneiss, each stage marking deeper burial and more intense compression. Minerals align, crystals stretch, and the rock records the memory of collision in its internal structure, like tree rings of catastrophe. The continents keep pushing. They do not know they have met. They cannot stop. Because plates are driven by forces far beneath them, convection currents inside Earth's mantle slowly circulating heat from the core outward. Continents are passengers on these currents. Once motion begins, it persists for tens of millions of years. Even after contact, the plates may continue converging for 50 million years or more. During this time, the collision zone expands wider and higher. Valleys form between rising ranges. Ancient seabeds are lifted above sea level. Marine fossils appear on mountain tops, silent proof that the highest land once lay beneath waves. Yet the collision is still not over. The two continents begin to weld together. At first they remain distinct blocks pressing against each other, but gradually sediments and melted rock fuse the boundary into a single larger landmass. The seam becomes harder to trace. Future geologists, millions of years later, will find fragments of oceanic crust trapped between them, the last remains of the vanished ocean. These fragments are clues, but the event itself is unimaginably slow. Human history fits inside a fraction of a millimeter of continental motion. All wars, inventions, empires, religions, languages, they occur while the continents move less distance than a coin's thickness. Yet the consequences outlast entire species. Because continental collisions do not only create mountains, they reorganize the planet. They alter atmospheric circulation, redirect ocean currents, reshape climates, and influence evolution itself. But at the beginning, the first chapter of every collision is simple. Two landmasses approaching each other across time. No explosion marks the moment. No sound announces the meeting. Only pressure, a pressure that never relaxes. Over millions of years, this pressure stores energy within the crust. Rocks bend like springs held under compression. When they finally snap, earthquakes occur, but these quakes are merely small releases compared to the total force involved. The true collision is too large to be expressed in a single event. Instead, it is expressed in geography. Where once there was ocean, there will be high plateau. Where once there was shoreline, there will be interior desert. Where one species evolved separately, they will meet. All because two drifting continents finally ran out of room. And even after they merge into one landmass, motion continues. The newly formed continent will begin breaking apart somewhere else millions of years later. Oceans will reopen, pieces will separate, but before separation comes union. And union begins here with a slow motion crash that reshapes the planet without anyone alive to witness its beginning. The Earth does not need sudden violence to transform itself. Given enough time, even the hardest stone flows. Continents travel across the globe like migrating giants, and every mountain range on Earth is a frozen record of one of these encounters. The Alps, the Himalayas, the Zagros, the Appalachians, each marks a place where land met land and refused to yield. This first stage is quiet, deceptively calm. No towering peaks yet dominate the skyline. No massive plateau stretches into the atmosphere. Only subtle uplift, folding, and deep internal change. But the collision has begun, and once begun, it cannot be reversed. The continents have chosen their path millions of years ago, carried by forces older than complex life itself. They will continue pressing together until the crust reshapes to accommodate them. Every second, they move closer. Every year, pressure increases. Every millennium, the landscape shifts imperceptibly, until eventually the world above can no longer remain unchanged. The slowest disaster in planetary history is underway, not destructive in a single moment, but transformative across ages. A crash measured not in seconds, but in epochs. And this is only the beginning. Before continents ever touch, before mountains rise, before earthquakes tear the land apart, an ocean has to disappear. Every continental collision begins, not with land meeting land, but with water slowly losing its place on Earth. Because two continents cannot collide while an ocean still separates them. And oceans, despite looking eternal, are temporary features. To us, oceans feel permanent. We grow up believing seas have always existed where they are now. The Indian Ocean, the Atlantic, the Pacific, they appear fixed on maps, part of the natural order of the world. But the seafloor is the youngest part of Earth's crust. While continental rocks can be billions of years old, most ocean floor rarely survives beyond 200 million years. Compared to continents, Oceans are constantly created and constantly destroyed. They live fast geological lives. At the center of oceans lie mid-ocean ridges, massive volcanic scars wrapping around the planet like stitches on a baseball. Here, molten rock rises continuously from the mantle and cools into new crust. Fresh seafloor is born, pushing older crust away from the ridge. This movement is slow but relentless. The ocean widens. Continents drift apart. For tens of millions of years, this is all that happens: separation. New water fills the growing gap. Marine ecosystems flourish. Life adapts to expanding shallow seas and deep basins. The ocean matures, but growth cannot continue forever, because Earth's surface area does not increase. If new crust forms somewhere, old crust must disappear somewhere else. That disappearance happens at subduction zones, long curved trenches where the seafloor bends downward into the mantle. These trenches are not small features. Some stretch thousands of kilometers across the planet. Here the ocean begins to die. The dense oceanic crust sinks beneath a continent or another ocean plate, pulled downward by gravity into the hotter, softer mantle below. As it descends, water trapped in minerals escapes upward, melting surrounding rock and feeding volcano chains above. Island arcs rise, volcanoes erupt, earthquakes shake deep below the water. From the surface, nothing seems unusual. Waves continue to roll, fish migrate as always, the horizon looks unchanged, but the ocean basin is shrinking. Imagine draining a lake by removing its bottom grain, by grain not visible at first, but inevitable. Over time, every year, a few centimeters of ocean floor vanish. Over 1 million years, kilometers disappear. Entire underwater mountain ranges are swallowed. Ancient coral reefs sink into darkness, crushed under pressure as they descend. Marine sediments that recorded the history of life slide into the mantle to be melted and recycled. The ocean loses its memory. This process continues for tens of millions of years. Continents that were once separated by thousands of kilometers gradually approach. At first, the narrowing is imperceptible. Later, coastlines migrate inward, shallow seas retreat. Weather patterns begin to change, and still, the ocean keeps dying. Eventually, the basin becomes narrow enough that life at the coasts feels its absence. Tides alter. Marine biodiversity declines as habitats shrink. Migratory routes collapse. Species that depended on wide-open water disappear. To human observers, if any existed, it would seem like climate change. But the real cause lies far below. As subduction continues, volcanoes along the continental margin grow taller and more active. Ash falls across nearby land. Lava reshapes coastlines. The air smells of sulfur. Earthquakes become frequent, but still not catastrophic. The continent is approaching another continent, and the ocean stands between them, thinning year by year. There was once such an ocean between Africa and Europe and Asia. It lasted over 100 million years. It supported massive marine reptiles, giant ammonites, and endless plankton blooms that painted the waters green. It was called the Tethys Ocean. Today, almost none of it exists. Fragments remain in the Mediterranean, Black Sea, and Caspian Sea, small survivors of a once vast body of water. The rest vanished beneath converging continents. The Himalayas exist because that ocean died. As the ocean floor continues subducting, something unusual eventually happens. The spreading ridge that created the ocean may itself approach the trench. When that occurs, the supply of new oceanic crust stops. No new floor forms, only destruction remains. From that moment, the ocean has entered its final phase. The distance between continents now closes rapidly in geological terms. Within a few million years, a brief moment in Earth history, the remaining seafloor disappears entirely. The trench reaches the continental margin. Water still fills the basin, but there is no longer any true oceanic crust separating the lands. Instead, sediments pile thickly between them, mud, sand, and biological remains accumulated over millions of years. These sediments are about to become mountains. But before mountains rise, the last act of the ocean unfolds. The final remnants of seafloor descend beneath the continent, carrying deep marine fossils, chemical signatures, and ancient life into the mantle. The volcanic arc above becomes unstable eruptions, intensify as the subduction angle changes. The planet prepares for impact. At last, the leading edges of two continents arrive at the trench simultaneously. Now the rules of subduction break. Oceanic crust could sink because it was dense. Continental crust is lighter and thicker. When it reaches the trench, it refuses to descend easily. The downward conveyor belt stalls. The subduction zone chokes. For millions of years, it had consumed ocean floor smoothly. Now it jams like gears forced together. Compression replaces descent. The sediments trapped between the continents begin folding upward into chaotic ridges. Deep marine rocks, once buried kilometers below water, rise toward the sky. Limestone containing shells forms the foundation of future mountains. The ocean has nowhere left to go, and so it disappears not by draining, but by being lifted out of existence. Water retreats as land rises. Shorelines shift outward. The former seabed becomes dry ground. Fish habitats turn into valleys. Salt deposits remain as proof of vanished seas. The death of an ocean is not dramatic in a single moment. No giant wave empties the basin. Instead, over thousands of generations, the water withdraws from advancing highlands. Where ships once sailed, rivers now flow. Where whales once migrated, glaciers may later form. Eventually, only isolated inland seas remain, trapped pockets of the former ocean cut off from global circulation. These gradually evaporate or fill with sediment. Their chemistry changes. Life inside becomes specialized, then often extinct. The ocean is gone, but its remains define the landscape forever. The rocks lifted during the collision preserve its history. Deep sea mud turned to shale, coral reefs transformed into marble, microscopic shells forming entire mountain ranges. If you climb certain peaks today, you walk across the floor of a vanished ocean. The highest mountains on Earth contain sea creatures older than mammals. That is the signature of ocean death. And only now, after millions of years of silent disappearance, can continents truly collide. Without the ocean between them, nothing absorbs the motion anymore. The kinetic energy that once pulled seafloor downward must now compress land upward. The stage is set. The sea is gone. The continents meet, and the world will never look the same again. The ocean is gone. For tens of millions of years, Earth had been quietly erasing the water that separated two drifting worlds. The sea floor descended into darkness. Volcanoes marked the boundary, and sediments piled between approaching lands. Now nothing soft remains between them. Only rock meets rock. And here the planet faces a problem it cannot solve the usual way. Because Earth has one simple method for dealing with moving plates. When two plates converge, one sinks. But continents do not. Oceanic crust sinks easily because it is heavy. It is thin, dense basalt forged from cooled lava, barely 7 kilometers thick in most places. Compared to continents, it is like iron compared to wood. Continental crust is different. It is made of lighter granitic rock and is far thicker, up to 70 kilometers deep in places. It floats higher on the mantle, much like icebergs floating in water. The deeper roots below continents make them buoyant, so when a continent reaches a subduction zone, the conveyor belt of the planet stops working. The slab tries to descend. It fails. Gravity pulls downward. Buoyancy pushes upward. Neither wins. Instead, the motion converts into pressure, and pressure has only one outlet: deformation. At the exact moment continents first touch, nothing visible happens on the surface. No explosion, no instant mountain range, no catastrophic rupture across the landscape. But deep underground, forces beyond imagination begin building. Two land masses, each hundreds of kilometers thick, continue moving toward each other because mantle currents still drive them forward. They do not know they have collided. They cannot stop simply because resistance appeared, so they push harder. The crust shortens. Rock that once occupied 1,000 kilometers horizontally must now fit into 800, then 600, then less. Stone cannot vanish. It must move, and so it bends. Layers of rock laid flat for hundreds of millions of years begin to ripple like fabric compressed from both ends. Sedimentary beds curve upward into arches and downward into troughs. These folds grow tighter with time. At first they are gentle hills. Later they become sharp ridges. Eventually they overturn entirely, flipping layers upside down so older rocks sit atop younger ones, reversing geological history. Entire sections of crust begin sliding over each other along massive fractures called thrust faults. One continent climbs over the edge of the other, not downward, upward. Kilometer-thick sheets of rock detach and travel tens of kilometers across the surface, riding atop neighboring crust like slow landslides frozen in time. These sheets stack repeatedly, thickening the land like layered armor. The ground is not breaking once. It is breaking continuously for millions of years. From above, if you could watch at extreme speed, you would see the planet wrinkle, not crack apart, compress inward. Valleys squeeze shut, plains buckle, ancient shorelines crumple into stone waves. What was once flat begins becoming complex beyond recognition. This process has a name: orogenic compression, the engine of mountain creation. But mountains are not the first result. Thickness is. As layers stack, the crust doubles its depth. A continent that was 35 kilometers thick may become 70 kilometers thick. Deep inside, temperatures rise because buried rock approaches the mantle. Pressure transforms the material itself. Shale becomes slate. Slate becomes schist. Schist becomes gneiss. Minerals realign under directional stress, forming patterns that geologists millions of years later will read like the memory of a battle recorded inside stone. The land is not just changing shape, it is changing identity. Meanwhile, something equally dramatic happens far below the surface. Because the crust has thickened, it pushes deeper into the mantle like the submerged root of a floating iceberg. This deep root stabilizes the forming mountain belt, allowing it to grow higher later. But for now, the surface remains deceptive. A human walking across this region during early collision would see hills and strange ridges, not towering peaks. Rivers would still flow across them. Life would continue almost normally. The catastrophe is too slow to notice. Civilizations could rise and fall entirely unaware they lived on a future mountain range. Yet stress keeps building. Rocks are strong, but not infinitely strong. Under constant pressure, they behave differently than expected. At shallow depth, they fracture earthquakes occur. At deeper levels, they flow like warm wax. The collision zone becomes layered behavior, brittle near the top, plastic below. The upper crust snaps repeatedly, forming fault systems hundreds of kilometers long. Each movement releases energy accumulated over centuries or millennia. But these earthquakes are only side effects. The real event is continuous, shortening, unstoppable convergence that forces land to occupy less space than it once did. Imagine compressing a thick book from both ends. The pages warp upward. Now imagine the pages are kilometers thick rock layers and the compression lasts 40 million years. The result is inevitable. Upward growth, because the only direction left is skyward. The continents cannot sink, so they rise, and the Earth begins building something that will outlive ocean. Deep beneath the surface, the collision has now entered a new phase. For millions of years, the continents have been pushing against each other, folding rock, stacking crust, and thickening the boundary between them. The ground above still shows only rugged hills and distorted landscapes, nothing yet resembling the tallest mountains on Earth. But underground, something critical is happening. The crust has become too thick to remain stable. Rock behaves differently under extreme pressure and temperature. At shallow depth, it fractures, producing earthquakes and faults. But deeper than about 15 to 20 kilometers, rock stops behaving like brittle stone. It begins to flow slowly, almost like tar, not liquid, not solid, but plastic. In this deep zone, the roots of the two continents begin to merge. Instead of sliding cleanly past each other, they interlock, massive blocks of crust pressed together, heating under pressure. Minerals recrystallize. Water trapped inside rock lowers melting temperatures. Portions of the lower crust begin to partially melt, forming pockets of magma far below the surface. This is not volcanic magma rising quickly toward eruption. This magma moves slowly, sometimes remaining trapped for millions of years, reshaping the internal architecture of the continent itself. The collision is no longer just mechanical. It has become thermal. As crust thickens further, gravity begins fighting back. A thickened crust is heavy, and although continental rock floats on the mantle, it can only float so high before instability occurs. The deep root pushes downward while the surface bulges upward. This imbalance causes lateral spreading. Some regions extend sideways even while the overall boundary compresses. The result is paradoxical. The collision both squeezes and stretches the land at the same time. Regions, not yet sharp mountains, but lifted terrain, thousands of meters above sea level. This is the earliest stage of a high plateau. Air becomes thinner, temperatures drop, Weather patterns begin shifting, but mountains still have not reached their final height, because height requires time and erosion. While the land rises, wind and rain attack it relentlessly. Every centimeter uplifted is carved away by rivers. Sediments eroded from the growing highlands fill surrounding basins, burying ancient landscapes under kilometers of debris. These basins sink under the accumulating weight, forming deep foreland depressions beside the collision zone. So while the center rises, the edges sink. This is how mountain systems widen, not as a single wall, but as a broad region of deformation spanning hundreds of kilometers. The continents are not touching at a line. They are merging across a vast zone, and that zone grows thicker, hotter, and higher. Inside the deep crust, partially melted rock begins migrating upwards slowly through fractures. Over millions of years, it cools into massive granite bodies called batholiths, cores of future mountain ranges. These rocks will not be exposed until erosion strips away kilometers of overlying material far in the future. Yet they form now, hidden beneath rising terrain. The collision writes its history in layers. At the top, fractured sedimentary rock, below folded metamorphic belts, deeper molten and recrystallized continental roots, a vertical record of unimaginable pressure. As compression continues, some parts of the crust fail catastrophically. Instead of bending, giant slabs detach and thrust tens of kilometers across neighboring land. Entire sections of continent override others, stacking repeatedly. Each thrust event may take hundreds of thousands of years, slow enough to seem motionless, yet unstoppable. If you stood on one of these slabs, you would never feel it move. But over 1,000,000 years, you would be transported across a distance greater than many countries. The land itself travels. This stacking process raises elevation steadily. Hills become ranges. Ranges merge into massive belts. Valleys deepen between rising ridges. River systems reorganize as slopes change direction. Drainage patterns flip entirely. Rivers that once flowed toward an ocean now reverse course toward an interior basin. Lakes appear and vanish repeatedly as uplift alters topography faster than water systems can stabilize. The geography becomes chaotic. Meanwhile, earthquakes continue endlessly. Not the singular catastrophic rupture people imagine, but countless moderate quakes occurring across a broad region. Each represents rock adjusting to pressure over millions of years. These adjustments collectively raise the land higher and higher. Every tremor is a tiny step upward. The collision has no single climax moment. Its violence is distributed across time. At last, after tens of millions of years, elevation reaches a tipping point. The thickened crust achieves enough buoyancy to support extreme altitude. The deep root stabilizes the mass above, allowing the surface to rise dramatically rather than just fold. Now mountains truly begin to appear. Not hills, not ridges, mountains measured in kilometers. But even now they are not finished, because the continents are still moving and they still cannot sink. By now, tens of millions of years have passed since the continents first met. Nothing about the landscape resembles its former self. Where there were once shallow seas and rolling plains, the crust has thickened into a colossal mass of rock pressing upward against gravity. The collision zone has widened into a vast region of deformation, stretching farther than a traveler could cross in a lifetime. And finally, the surface can no longer hide it. The mountains emerge. At first, they appear as scattered ranges separated by high valleys, but compression never stops. Every year, imperceptible to living beings, the plates continue moving millimeters closer. The deep crust keeps shortening horizontally, forcing more material upward. Peaks sharpen, valleys deepen. Glaciers begin forming at high elevations, carving into the rising rock and accelerating erosion. Ice becomes a sculptor, slicing through young mountains, exposing fresh stone beneath. The faster erosion removes weight from above, the more buoyant uplift occurs from below, a feedback loop between destruction and creation. The mountains rise because they are being worn away. Without erosion, the crust would thicken but not reach extreme height. Removal of mass allows deeper rock to float upward like an iceberg adjusting in water. So paradoxically, rain, wind, and ice help build the tallest peaks on Earth. Deep below, the continental route has now doubled its original thickness. It plunges into the mantle like a keel beneath a ship, stabilizing the towering mass above. This route is invisible from the surface, but essential. Without it, the mountains would collapse under their own weight. The entire region now behaves as one welded continent. The boundary where the ocean once existed has transformed into a suture zone, a scar made of crushed seafloor remnants, metamorphosed sediments, and fragments of both continents fused together. Rivers reroute around rising barriers. Ecosystems split apart by altitude differences. Species isolated on opposite sides of the mountains begin evolving independently. Climate patterns shift as the new terrain blocks atmospheric circulation. The collision reshapes biology as much as geology. Earthquakes remain constant companions to this process. Because the continents still attempt to move through each other, stress accumulates endlessly along massive fault systems spanning thousands of kilometers. These faults do not mark a single break, but an entire network of fractures, each accommodating a fraction of the motion. No single earthquake releases all the energy. Instead, countless earthquakes occur across millions of years. The mountains are, in a sense, frozen earthquakes, the permanent record of motion that could never fully happen sideways, so it happened upward. As uplift continues, something extraordinary becomes visible. Rocks that formed at the bottom of the ocean now stand near the sky. Limestone containing marine shells appears kilometers above sea level. Deep marine clay transformed into slate forms ridges. Fossils of microscopic sea organisms are found embedded in mountain summits. The highest land on the planet was once seabed. This is not poetic metaphor, it is literal geological history. The ocean did not retreat from the mountains rose from the ocean. But even these towering peaks do not represent the end of collision, because the continents are still converging. Over time, compression slows but does not cease. Instead of increasing height indefinitely, the system reaches equilibrium. The crust cannot thicken forever. Gravity forces it to spread sideways. The plateau broadens. New faults develop farther from the center. The active deformation zone migrates outward. Mountain building evolves into mountain maintenance. From now on, uplift and erosion balance each other. Peaks grow slowly while being carved away at nearly the same rate. The landscape enters a long-lived state, lasting tens of millions of years, a stable but restless highland. The collision has achieved its maximum expression, a mountain belt stretching thousands of kilometers across the planet. Eventually, mantle currents will change direction. The compressive forces will weaken. The welded continents will behave as one rigid block. Earthquakes will decrease in frequency. Erosion will gradually lower the peaks. Given enough time, perhaps 200 million years, the mountains will almost disappear. Future civilizations, if any exist, might see only gentle hills where immense ranges once stood. The record of collision will remain buried deep underground, and somewhere else on Earth, new oceans will close. New continents will meet. The cycle will repeat, because continents never truly stop moving. They only pause between collisions. And whenever land refuses to sink, the sky must rise to make room. For millions of years, the continents have pressed against each other. Rock folded, crust thickened. The ground rose slowly. But until now, the transformation remained mostly hidden hills, plateaus, and broken terrain, hinting at something larger beneath the surface. Now the planet crosses a threshold. Elevation accelerates. The mountains are finally born. A mountain range does not appear all at once. There is no moment where flat land suddenly becomes towering peaks. Instead, mountain birth is a gradual victory of uplift over gravity. For tens of millions of years, the crust has been thickening underground like a swelling bruise beneath skin. Eventually, the thickened crust becomes buoyant enough to lift entire regions dramatically upward. The land rises kilometers into the atmosphere. Air pressure drops. Temperatures fall. Weather changes instantly. Where forests once grew, alpine tundra begins forming. Rivers steepen and cut violently downward, carving deep valleys faster than ever before. Water accelerates, carrying enormous sediment loads towards surrounding lowlands. The world has entered the age of vertical geography. The first true mountains are not sharp peaks, but vast highlands, immense plateaus, lifted thousands of meters high. Their surfaces remain relatively broad, yet their edges collapse into steep escarpments. These elevated plains mark the newborn stage of a mountain system. From a distance, the terrain resembles a continent lifted onto a pedestal. But uplift continues, because the plates are still converging. Each year, perhaps only a few millimeters of additional height is gained. No living creature notices. Yet over 1 million years, that becomes a kilometer. The sky moves farther away from the ground. As the land climbs higher, the atmosphere begins interacting differently with it. Air masses forced upward over the rising terrain cool and release moisture. One side of the mountains receives relentless rainfall, feeding glaciers and rivers. The opposite side becomes dry, trapped in the shadow of the peaks. The mountains create climate divisions. Two ecosystems, separated by only a few hundred kilometers, begin evolving entirely different worlds. On one side, dense forests and heavy rain. On the other, deserts and barren plains. The collision is no longer only geological. It has become environmental. But mountains do not grow smoothly. Their growth is violent, just slow. As uplift increases slope steepness, gravity constantly destabilizes the terrain. Entire cliffs collapse in landslides the size of cities. Valleys deepen rapidly as rivers gain energy from elevation. Erosion attacks the mountains as quickly as they rise. This seems contradictory, yet it is essential, because mountains cannot grow tall without erosion removing weight from above. When material is stripped away, the deep crust rebounds upward. The more erosion occurs, the more uplift follows. The tallest peaks exist where destruction is strongest. Meanwhile, deep beneath the surface, molten rock slowly ascends through fractures formed by compression. These magmas cool underground, creating massive granite cores, the hidden skeleton of mountain ranges. Millions of years later, erosion will expose these hardened interiors as towering spires and jagged peaks. What we recognize as dramatic mountain landscapes are actually the roots of even larger mountains that once stood above them. Mountains reveal their insides over time. The sharper they look, the older they are. Young mountains appear broad and rounded. Ancient mountains appear rugged and skeletal. The collision continues, pushing upward. Individual ranges merge into chains stretching across continents. Valleys align along fault zones. River systems reorganize entirely, sometimes reversing direction as uplift tilts the land. Entire drainage networks collapse and reform. Lakes appear high above sea level, temporary inland seas trapped by rising ridges. Over time, they fill with sediment and become plateaus themselves. Nothing in the region remains stable long enough for permanence. Yet compared to human time, it feels eternal. Glaciers now dominate the highest elevations. Snow accumulating year after year compresses into ice, which begins flowing downhill under its own weight. These glaciers grind the mountains relentlessly, carving U-shaped valleys, cirques, and knife-edge ridges. The mountains are sculpted as they are built. Without ice, they would look entirely different. Glacial erosion sharpens peaks into dramatic forms, pyramids and horns rising above the landscape. The beauty of mountain scenery is the result of slow destruction acting upon slow creation. Every peak is shaped by loss. As elevation increases further, the mountains begin affecting global climate systems. They block planetary wind circulation, redirect monsoon patterns, and alter ocean currents by changing atmospheric pressure zones. Rainfall distribution across entire continents shifts. Regions thousands of kilometers away feel the consequences. A collision between continents becomes a planetary event, and still the land rises. The mountain range now stretches farther than the eye could ever see a scar across the earth, visible even from space. Peaks climb into the jet stream, interacting with high-altitude winds that erode them from above, while rivers erode them from below. The planet is balancing forces. Mantle pushing upward, gravity pulling downward. Climate wearing sideways, the mountains exist at the intersection of all three. But the highest peaks have not yet formed, because extreme height requires time and continued pressure. The continents still move, and the sky has not yet reached its limit. The mountains have risen high enough to change the sky. Clouds that once drifted freely across the region now encounter a war, stretching for thousands of kilometers. Moist air climbs the slopes, cools and releases rain in enormous quantities. Rivers swell beyond anything the land once carried. On the windward side, water dominates. On the far side, dryness spreads. The mountains create a rain shadow, a silent climatic divide. Vast deserts begin forming where forests might otherwise exist. Grasslands expand. Entire ecosystems shift position across the continent, all because rock has risen upward. The atmosphere reorganizes around the terrain, but the mountains are still growing. As the crust continues thickening, the highest elevations enter the upper troposphere. Here, temperatures remain permanently low, even in warm planetary eras. Snow accumulation becomes year-round at the summits. Permanent ice caps appear. These are not polar ice sheets. They exist at the equator if the mountains are tall enough. Elevation replaces latitude as the controller of climate. Ice begins to reshape the landscape at a new scale. Glaciers advance down valleys, carving deep troughs and transporting enormous quantities of rock outward into surrounding basins. Sediments carried from the mountains form massive alluvial fans and floodplains far below. Lowlands become fertile because mountains exist. Without uplift, rivers lack the energy to carry nutrients. The growth of complex ecosystems downstream depends on the constant grinding of rock high above. Mountains feed life below them, but glaciers do more than transport sediment. They control erosion rates. Where ice covers peaks, erosion slows, allowing further uplift beneath. Where ice melts seasonally, meltwater cuts rapidly downward, deepening valleys faster than the surrounding terrain rises. The result is dramatic relief. Sharp peaks and deep gorges appear side by side. Vertical differences reach several kilometers within short horizontal distances. Landslides become common, triggered by earthquakes still rippling through the collision zone. Nothing here is stable for long. Even the tallest mountains are temporary shapes. Deep inside the crust, pressure continues transforming rock. The lower layers, once buried sediment, now exist under conditions approaching those of the mantle. Minerals rearrange into high-pressure forms. Some rocks melt partially and move upward, forming domes beneath the surface. Over time, these domes push upward and fracture the overlying layers, creating new peaks. The mountains rise not only by compression, but by buoyant expansion from below. They are lifted from beneath as much as they are squeezed from the sides. This internal inflation helps explain why certain ranges remain elevated for tens of millions of years. Their roots are dynamically active long after collision slows. The mountain chain now dominates the continent. Weather systems circle around it. Ocean currents shift because atmospheric pressure belts relocate. Seasonal winds strengthen on one side and weaken on the other. Monsoon patterns can be born from mountain uplift alone. Moist air, pulled inland, meets the barrier, rises, cools, and falls as rain across huge regions. Agricultural zones, forests, wetlands, all may owe their existence to a distant tectonic collision millions of years earlier. The planet's climate is rewritten in stone. As elevation continues, something unusual happens to rivers. Instead of flowing across the mountains, many become trapped within them. Valleys deepen faster than uplift can raise ridges, locking rivers into fixed paths. These rivers carve canyons that cut directly through rising peaks. The mountains grow around the rivers rather than redirecting them. This produces gorges, thousands of meters deep, scars of persistent water cutting through rising rock over millions of years. The landscape becomes three-dimensional in the extreme. Meanwhile, erosion deposits enormous sediment layers around the base of the mountains. These foreland basins sink under the weight of accumulating debris. New plains form flat, fertile lands that contrast sharply with the jagged terrain nearby. The collision therefore creates two environments simultaneously: towering highlands, expansive lowlands. Civilizations in the future often arise in the latter, nourished by minerals eroded from the former. Mountains create the conditions for life far beyond their slopes. But the collision has not stopped. Even as peaks reach extraordinary heights, the plates still converge slowly. Each million years adds a little more elevation before erosion removes it again. The mountains exist in balance, never fully growing, never fully shrinking. They are dynamic structures. And at last, some peaks rise above 8 kilometers. Air pressure here is less than a third of sea level. Oxygen is scarce. Temperatures remain below freezing most of the year. Only specialized organisms survive. The planet has created an environment almost extraterrestrial compared to surrounding land. The birth of giant mountains is complete, yet their influence is only beginning. The mountains now stand at their greatest height. From lowland plains they appear almost unreal, a horizon of stone walls rising into thin blue air, peaks catching sunlight long after the valleys fall into shadow. Storms gather around them as if orbiting. Winds accelerate across passes. Snow never fully melts from the highest summits. What began as invisible compression underground has become one of the most dominant features a planet can produce. A continental scale mountain chain, but reaching maximum height does not end their story. Because mountains are not monuments, they are processes. Even as the peaks tower skyward, gravity begins its slow victory. Rock at high elevation possesses enormous potential energy. The higher the mountains rise, the stronger erosion works to bring them down. Rainwater penetrates fractures and freezes, expanding and breaking apart cliffs. Glaciers grind valleys deeper. Rivers transport the debris outward. Every grain removed reduces weight from above, and every reduction in weight triggers uplift from below. This balance is called Isostasy, the floating equilibrium of Earth's crust on the mantle. Remove mass, and the crust rises slightly. Add mass, and it sinks. So, mountains do not simply erode downward, they rebound upward while eroding. For tens of millions of years, peak elevations may remain nearly constant, even though entire kilometers of rock are removed. The mountains maintain their height by continuously exposing deeper material. What stands at the surface today may once have been buried far below. The visible peaks are actually the middle layers of an ancient vertical structure. Deep within the range, rocks formed under immense heat and pressure slowly reach daylight. Minerals that crystallize 20 or 30 kilometers underground become exposed at the surface, telling the story of the collision in microscopic detail. Geologists millions of years later will study these rocks and discover the temperature, depth, and force involved in their creation. Each crystal lattice holds memory, a record of continental impact, preserved long after the mountains themselves vanish. Because eventually they will vanish, but not soon. At maturity, the mountain system becomes part of the planet's permanent geography. The continents have now fully welded together. The former ocean basin exists only as fragments, trapped between them serpentine rocks, marine limestones, and metamorphosed sediments marking the seam. This line is called a suture zone, the scar of planetary scale collision. Across this scar, earthquakes still occur, not as violently as during early compression, but persistently. The continents remain under residual stress. Even long after uplift slows, adjustment continues. Mountains settle very slowly. Climate stabilizes around the range. Moisture patterns become predictable. Glacial cycles advance and retreat across high elevations. River networks mature, carving recognizable valleys. Soil forms across lower slopes, allowing forests to expand. Life adapts fully to the presence of altitude. Species evolve, specialized traits, thicker fur, efficient respiration, cold tolerance, slope mobility. Some animals remain confined to one side of the mountains, separated for millions of years from relatives on the other side. The range becomes an evolutionary barrier. Entire ecosystems owe their existence to the fact that land once refused to sink beneath land, yet deep below, the mantle continues moving. The forces that drove the collision weaken gradually as plate motion changes direction. Compression slows, uplift decreases, erosion begins to dominate more strongly than rise. The mountains have entered old age, peaks lower slightly, slopes soften, valleys widen, the sharpest ridges become rounded, glaciers retreat as elevation decreases, rivers meander more gently. Given enough time, perhaps 100 to 200 million years, the range may shrink to rolling hills. Future inhabitants might never imagine that these gentle landscapes were once among the tallest mountains on the planet. But the crust will remember, because continents do not stay assembled forever. Eventually, new rifts will open somewhere far away. Mantle currents will pull the unified landmass apart. New oceans will form. The cycle of drifting begins again. And someday, distant fragments of this same continent may collide once more, creating a new mountain system built partly from the eroded remains of the old one. Mountain birth is not a single event in Earth history. It is a recurring chapter. From the death of an ocean to the refusal of land to sink, to the rise of peaks touching the atmosphere, giant mountains represent the planet solving a problem of motion. There was nowhere else for the rock to go. So the sky made space. Mountains look permanent. They rise above clouds, survive storms, outlast civilizations, and appear immune to change. To anyone living beside them, they feel like the most stable structures on Earth, but mountains are not stability. Mountains are pressure, and pressure never rests. Even after the continents have fully collided, even after the ocean has vanished, even after the peaks have reached their greatest height, the motion continues. Because tectonic plates do not stop moving the moment they meet resistance. The forces pushing them originate deep inside Earth, slow convection currents circulating heat from the core through the mantle. These currents persist for billions of years, so the continents remain locked together while still trying to move. The result is not constant motion. The result is constant strain. Imagine pressing your hands together as hard as you can. They do not slide smoothly. They stick, muscles strain. Friction holds them in place. Energy builds in silence. Nothing moves until suddenly your grip slips and your hands jerk forward. That sudden release is tiny in your muscles. Inside Earth, it becomes an earthquake. Along the collision zone, the crust is fractured into enormous blocks separated by faults, deep cracks, sometimes extending tens of kilometers downward. These faults are not clean breaks, but jagged surfaces where rock grips rock under immense pressure. For years, decades, centuries, they do not move. But the plates keep pushing. Each year, the stress increases. Rocks deform microscopically, crystals bend, internal friction rises. The landscape above appears peaceful. Forests grow, rivers flow, people build cities. Yet underground the strain accumulates like a compressed spring. Eventually, friction fails. The fault slips. and in seconds, centuries of motion occur at once. The ground shakes because the rock does not move smoothly, it snaps from one locked position to another. Energy radiates outward through the crust as seismic waves, traveling faster than sound, passing through mountains, plains, and oceans alike. This is not the collision itself. This is only adjustment. The true motion took centuries. The earthquake is merely its sudden correction. In continental collision zones, earthquakes behave differently than at ocean trenches. At subduction zones, where oceanic crust dives into the mantle, earthquakes often occur deep below the surface. But where continents meet, the crust is thick and buoyant. The stress remains trapped near the surface. So earthquakes here are shallow, and shallow earthquakes are dangerous, because the energy does not dissipate before reaching the ground above. Cities near collision boundaries sit directly atop stored geological force. When release occurs, the shaking is violent. Buildings collapse not because the magnitude is always greatest, but because the energy is delivered directly beneath them. Mountains hide tension beneath their beauty. The important detail is this: the collision never truly ends. Even 50 million years after first contact, the plates may still converge several millimeters per year. Over a human lifetime, the distance is small. Over 1,000 years, it is meters. Over geological time, it is enormous. But faults do not release motion continuously. They lock, and locking means future earthquakes are guaranteed. The interval between large earthquakes can be hundreds of years, long enough for entire civilizations to forget the last one happened. Buildings rise again in the same place, memory fades into myth, then the ground moves, not randomly but inevitably, because the stress never disappeared. It was only waiting. Each earthquake redistributes pressure along neighboring faults. Some regions relax, while others become closer to failure. The mountain belt behaves like a chain reaction system. Motion in one segment alters the entire network. This is why earthquakes often come in sequences. Not aftershocks alone, but long-term cascades across decades or centuries. A rupture in one region increases strain in another. The continent is constantly adjusting its internal balance. The mountains are still being built, just not visibly. Deep beneath the range, rocks at high temperature flow slowly, absorbing part of the motion. But near the surface, cold, brittle crust must fracture instead. This difference creates a layered seismic structure. Deep crust flows quietly. Upper crust breaks violently. The boundary between them defines the depth where earthquakes stop occurring. Beyond that, rock bends instead of snapping. In continental collision zones, that boundary lies relatively shallow, concentrating destruction near the surface. Yet earthquakes also play a role in shaping the mountains themselves. They lift ridges slightly higher, drop valleys slightly lower, offset rivers, create landslides that reshape slopes overnight. A single major quake can move a mountain face several meters in seconds, more change than centuries of erosion. The landscape evolves in bursts. Between earthquakes, the mountains appear eternal. During earthquakes, they reveal they are alive. Some faults extend for thousands of kilometers across continents. They mark ancient sutures where the ocean once existed, scars from the original collision. Even after mountains stabilize, these faults remain zones of weakness. Future plate movements reuse old fractures. Earth remembers where it once broke. And so earthquakes return again and again to the same regions across tens of millions of years. Not because the mountains are unstable, but because they are unfinished. The collision created the mountains. The earthquakes maintain them. Between earthquakes, nothing seems to happen. Decades pass. Generations grow old. Cities expand across valleys carved long before memory. The mountains stand silent, but silence is misleading, because while the ground does not move suddenly, it is always moving slowly. In a continental collision zone, the plates continue converging year after year. The motion is tiny, perhaps the width of a fingernail annually, but it never stops. Since faults remain locked by friction, the crust must deform elsewhere. So the land bends. Survey instruments placed across mountain belts often detect gradual motion. Slopes tilting, ridges creeping, valleys shortening. This movement is almost impossible for human senses to detect, yet it steadily stores elastic energy within the rock. The entire region behaves like a compressed spring, and springs do not remain compressed forever. When enough stress accumulates, a fault finally overcomes friction. The rupture does not happen all at once along its full length. Instead, it begins at a single point, a microscopic failure, where rock strength is exceeded. From there, a fracture front races outward faster than a passenger jet, tearing through the crust. As it travels, rock masses shift meters within seconds. Energy stored for centuries converts instantly into motion. Seismic waves radiate outward in every direction, compressional waves pushing and pulling the ground, shear waves shaking it side to side, and surface waves rolling like ripples across water but through solid stone. The ground behaves briefly like liquid. Near the rupture, the landscape may permanently change. Rivers jump their banks as their channels shift sideways. Roads offset suddenly. Cliffs collapse in cascading landslides. Entire slopes detach and move downslope, damming valleys and creating temporary lakes. Mountains adjust their shape, not gradually, but violently. Yet even these dramatic events are only small corrections compared to the total force driving the continents together. After the earthquake, the plates have moved only a fraction of the distance they attempted to travel. The remainder begins accumulating again immediately. The cycle restarts the moment the shaking stops. Because earthquakes do not release all the stress, they only redistribute it. Sections of the fault that slipped are now relaxed, but neighboring segments become closer to failure. Over decades or centuries, those areas may rupture in turn. The mountain belt experiences a chain of adjustments across time. To human history, these appear as separate disasters. To Earth, they are part of a continuous motion. Sometimes multiple faults rupture together. When this happens, the earthquake becomes enormous, not because the ground moves faster, but because a much larger area moves simultaneously. Hundreds of kilometers of crust may shift within minutes. The mountains tremble from end to end. These rare events reshape entire regions. Landslides block rivers, creating lakes that may last centuries. Valleys sink slightly, altering drainage networks permanently. New springs appear where groundwater pathways changed deep underground. The terrain reorganizes itself. But the most important effect lies deeper. Each major earthquake subtly modifies the stress field inside the crust. Some regions become more stable for a time, while others edge closer to their breaking point. Predicting the next rupture becomes extremely difficult because the system is interconnected. The mountains function like a network of loaded beams, change tension in one place and another reacts. This is why seismic activity can migrate along a mountain range over centuries. The collision never pauses long enough for equilibrium. Even when earthquakes are absent for long periods, motion continues invisibly. Geologists call this strain accumulation the slow storage of energy in rock. The longer a fault remains locked, the larger the potential future earthquake becomes. Ironically, the quietest regions may be the most dangerous, because silence means pressure has not been released. Over millions of years, this repeated cycle builds the topography we recognize today. Without earthquakes, the mountains would relax and spread outward more smoothly. Instead, periodic ruptures keep slopes steep and relief dramatic. Sharp ridges and deep valleys owe their existence partly to sudden vertical offsets during seismic events. The beauty of mountain scenery is tied to violent adjustment. Every dramatic cliff may be the product of ancient earthquakes, lifting one side higher than the other. Even after plate convergence slows, earthquakes persist. The crust remembers its deformation. Residual stresses remain locked inside for tens of millions of years after major collision phases end. Old faults reactivate under new stress directions. Regions long considered stable awaken again. The mountains age, but they never become completely still, because once continents have collided, the internal structure of the crust is forever complicated, fractured, layered, and prone to future movement. In this way, continental collisions leave a permanent seismic inheritance. Long after peaks erode into hills, long after rivers cut through the range, the ground may still shake, not because a new collision has begun, but because the last one never fully ended. Across human history, earthquakes feel sudden. They strike without warning, last seconds, and leave permanent memory. Entire cultures record them as singular, catastrophic moments the day the ground betrayed stability. But to Earth, an earthquake is not an event. It is a symptom, because the real motion is always happening between earthquakes. Millions of years pass inside a collision zone, much the way centuries pass for us in cycles. Periods of relative calm interrupted by brief, violent adjustment. After each rupture, landscapes settle temporarily, only to begin storing stress again. If a time-lapse camera could observe a mountain belt across 10 million years, the pattern would become clear. Long stillness, sudden movement, long stillness, sudden movement, again and again. The mountains breathe in slow geological pulses. Early in the collision, earthquakes are frequent and powerful because the crust is rapidly shortening. Faults are young, rough, and irregular. They lock strongly and release large amounts of energy when they fail. But as millions of years pass, the system evolves. Fault surfaces grind against each other repeatedly, smoothing their contact points. Broken rock accumulates along them as crushed material called fault gouge, which can act like a lubricant. Some faults begin creeping slowly rather than locking completely. The violence decreases. Not immediately, but gradually, across immense spans of time. The mountain belt begins calming. This does not mean earthquakes stop. They change character. Instead of enormous ruptures spanning hundreds of kilometers, the region experiences many moderate quakes distributed across a wider area. Stress spreads into secondary fractures. The crust learns to accommodate motion more efficiently. In geological terms, the collision matures. The plates are still moving, but the mountains have adjusted to the pressure. They now deform with less resistance than before. The system approaches balance. Eventually, plate motion shifts elsewhere on the planet. Mantle convection redirects forces toward new boundaries. The welded continent becomes part of a stable interior rather than an active edge. Compression slows to almost nothing. The mountains enter true old age. Earthquakes grow infrequent. When they occur, they often reactivate ancient faults rather than create new ones. The landscape changes little from each event. Rivers remain in place. Valleys no longer deepen dramatically. Slopes weather gently instead of collapsing violently. Time overtakes tectonics. Yet the memory of motion never vanishes entirely, because the crust remembers every stress it has experienced. Even in stable continental interiors, ancient collision zones can awaken after hundreds of millions of years if new forces arise. A distant rift or plate boundary may transmit stress across thousands of kilometers, finding weakness in old sutures. Then the ground shakes again, a faint echo of a collision long finished. To observers living there, the earthquake seems mysterious, far from any plate boundary. But deep below, the fault formed when continents first met is still present, still capable of movement. The past never fully releases its hold on the crust. Over enough time, erosion lowers the mountains to hills. The great peaks disappear, glaciers vanish, rivers meander across wide valleys, forests cover slopes once too steep for soil. The dramatic landscape pact survives long after its surface expression fades, and with it, the possibility of earthquakes. So the story of a continental collision does not end with mountain building. It continues in the quiet trembling of the land for hundreds of millions of years, a slow fading of violence rather than a sudden stop. Each quake is a reminder that mountains were never static objects, but the visible crest of ongoing planetary motion. The land beneath them has always been adjusting, always settling, always remembering. Because when continents collide, the energy involved cannot be released in one moment, or one millennium, or even one era. It releases piece by piece across ages. Mountains are stone returned again in steady cycles. Climate followed latitude more than geography. Equator warm, poles cold. Everything in between gradual and predictable. The planet breathed smoothly. Then the land rose into the sky, and the atmosphere struck stone. Air is invisible, yet it behaves like a fluid ocean above us. Winds flow around the globe, guided by temperature differences and planetary rotation. Normally they curve gently across landscapes, but when they meet a mountain range stretching thousands of kilometers, they cannot pass through. They must go over. As air climbs, pressure drops. Expanding air cools. Cooling air releases water vapor. Cloud dries. This is called a rain shadow, and it transforms entire continents. Within a few million years of uplift, one side of the mountains becomes lush and fertile, while the other becomes arid or desert. The difference can be extreme jungles facing barren plains separated only by a wall of rock. The mountains divide climate more effectively than oceans ever could. The collision has begun rewriting weather, but the change does not remain local. High mountains alter planetary circulation patterns. Jet streams, fast-moving rivers of air high in the atmosphere, are forced to bend around the elevated terrain. Storm tracks shift thousands of kilometers. Seasonal rainfall migrates to new regions. Monsoon systems can be born from mountains alone. When land heats during summer, warm air rises above it, drawing moist ocean air inland. If a massive mountain barrier blocks that air, the moisture condenses rapidly, producing intense seasonal rains. Without mountains, the same winds would pass without releasing water. So the collision creates seasons where none existed before. Entire ecosystems depend on this. Temperature patterns change as well. High plateaus cool the atmosphere above them. Cooler air sinks outward into surrounding regions, lowering temperatures far beyond the mountains themselves. Ice sheets may form at latitudes previously too warm for glaciers. Over millions of years, global climate can shift toward cooling simply because enough rock rose high enough. Mountains help create ice ages. At the same time, erosion accelerates. Rain falling on fresh rock triggers chemical reactions that remove carbon dioxide from the atmosphere. The exposed minerals react with dissolved CO2 and lock it into solid compounds carried to the oceans. Less carbon dioxide means less greenhouse warming. The planet cools further. A geological collision becomes a chemical thermostat. The feedback continues. Higher mountains, more rain, faster erosion, less CO2, cooler climate, expanding ice, stronger erosion. The world's temperature may drop for tens of millions of years, following a major continental collision. The atmosphere is not independent of geology, it obeys it. Meanwhile, inland regions far from the mountains experience new extremes. With moisture blocked at the barrier, continental interiors dry and temperature swings grow severe. Hot summers, freezing winters, climates once moderated by ocean influence become harsh and seasonal. Grasslands replace forests. Dust storms become common. New habitats appear where none existed before. The rising mountains reorganize life across thousands of kilometers. The collision did not merely create peaks, it created weather. As the mountains grow higher, the atmosphere does more than release rain. It begins to reorganize the planet's heat. Earth's climate is driven by imbalance. The equator receives more solar energy than the poles. The atmosphere and oceans constantly move this heat around, trying to equalize temperature differences. Normally, air circulates in large, smooth cells across continents, but a continent-scale mountain range interrupts that balance. Instead of flowing north and south freely, air masses are forced upward and sideways. Entire circulation cells shift position. Regions that once lay inside warm, tropical airflow may suddenly find themselves under cool, descending air from high elevations. The geography changes the physics of the sky. High plateaus are especially important. Unlike narrow mountains, plateaus cover enormous areas, at altitude effectively lifting part of the Earth's surface into colder atmospheric layers. These elevated surfaces cool the air resting above them, creating persistent, high-pressure systems. From these high-pressure centers, dry, cold air spreads outward seasonally. Winters grow harsher across surrounding continents. Snowfall patterns migrate. Storms take new paths. Some regions experience heavier snowfall, while others lose precipitation entirely. The mountains begin controlling seasons across hemispheres. Oceans respond as well. Wind patterns drive ocean currents. When winds shift, currents shift. Warm water that once flowed towards certain coastlines may be redirected elsewhere. Cold currents may intensify or weaken. Coastal climates transform. A warm coastline can become foggy and cold within a few million years. A temperate region can become humid and tropical. Marine ecosystems adapt or collapse depending on nutrient circulation altered by these currents. Thus, a collision deep inland can affect fisheries thousands of kilometers away. The sea answers the mountains. Meanwhile, glaciers expand in high elevations and begin influencing sea level. Though continental collisions do not instantly freeze the world, they create conditions favorable for long-term cooling. Persistent ice at altitude reflects sunlight back into space. As cooling spreads, polar ice sheets may grow larger. Sea levels slowly drop. Shallow seas retreat from continental margins. Land bridges appear between previously separated regions. Animals migrate across them, mixing ecosystems that evolved apart for millions of years. Geography reshapes biology again, but now through climate rather than terrain. Dust becomes another powerful force. Newly formed dry basins near the mountains produce enormous quantities of fine sediment. Winds carry this dust across oceans, fertilizing distant marine regions with minerals that stimulate plankton growth. More plankton absorbs more carbon dioxide. Cooling strengthens. A mountain range can influence atmospheric chemistry across the globe. Over tens of millions of years, these combined effects stabilize into a new planetary climate regime. Rain belts settle in different latitudes. Deserts expand where moisture cannot reach. Wet monsoon regions support dense forests and eventually agricultural civilizations. Seasonal contrasts intensify in continental interiors. The world becomes more varied. Before the collision, climate followed latitude. After the collision, climate follows topography. Mountains rewrite the rules. Even when erosion later lowers the peaks, the climate does not instantly return to its former state. Ocean currents, atmospheric composition, and ice distribution may have already shifted into a different equilibrium. A single geological event can permanently redirect planetary evolution. The continents changed position. The air changed behavior. The oceans changed flow. And life must change with them. The collision that began as silent pressure beneath the ground has now reached the sky itself. The atmosphere has been reshaped by stone. By now, millions of years have passed since the continents first met. The mountains stand high, but their greatest influence is no longer the height of their peaks, it is the stability of the new climate they created. Because once atmospheric circulation changes long enough, life adapts to it, and adaptation makes change permanent. Forests grow where seasonal rains arrive predictably each year. Grasslands dominate where moisture comes only briefly. Deserts expand where mountains block clouds completely. Over time, ecosystems organize themselves around the new wind patterns as if they had always existed. Future species evolve, assuming this is normal. No animal living there remembers the time before the mountains rose. Yet the climate they depend on exists only because continents collided. Rivers also lock into new long-term paths. Fed by consistent rainfall on one side of the mountains, massive river systems develop, carrying sediments across entire continents. Floodplains build gradually, layer upon layer. forming fertile soils capable of supporting dense biological communities. Many of the world's most productive regions ultimately trace their origin to erosion from uplifted terrain. Without constant grinding of rock at altitude, minerals would not replenish the land below. The mountains nourish distant plains. Meanwhile, regions in the rain shadow develop their own stability, dryness. Lakes evaporate faster than they fill. Salt accumulates in basins. Wind shapes dunes that migrate slowly across open ground. Temperature swings become extreme. Hot days, cold nights, sharp seasonal contrasts. Life here becomes specialized, resilient, efficient with water. Two completely different worlds now exist side by side because air was forced upward millions of years earlier. Over even longer time spans, the atmospheric changes influence planetary ice cycles. Lower carbon dioxide from weathering reduces greenhouse warming enough that polar ice sheets expand during cooler orbital phases. Glacial periods become more pronounced. Ice advances and retreats rhythmically, shaping landscapes far from the original collision zone. The mountains indirectly control future ice ages. The Earth's long-term climate sensitivity increases because elevated terrain helps remove carbon from the air faster than volcanic processes replace it. Geology moderates temperature. Eventually, erosion begins lowering the mountains. Peaks shrink kilometer by kilometer across tens of millions of years. Glaciers retreat to higher altitudes. Rainfall patterns weaken slightly as the barrier lowers, but the planet does not revert fully. Ocean currents have adjusted, ice sheets have stabilized, atmospheric composition has changed, ecosystems have spread according to the earlier climate regime. The world carries forward the consequences of the collision even after the mountains fade. In this way, continental collisions influence the future far longer than the past. The mountains themselves may survive 100 million years. Their climatic legacy may last twice that. Even after the range erodes into hills, rainfall belts, deserts, and seasonal winds shaped by the uplift may persist because the broader planetary system has adapted to them. The collision becomes part of Earth's background condition, a permanent chapter written in air rather than stone. Eventually, new tectonic events elsewhere reshape the planet again. Another ocean opens, another closes, another mountain chain rises, somewhere distant, climate shifts once more. But every new state inherits traces of older ones. The planet's atmosphere is cumulative history, a layered memory of ancient geography. Every breath taken by future life will contain molecules once locked into rock during a collision long forgotten. The mountains began as pressure underground. They ended as weather overhead. From the first uplift to the final erosion, they governed rainfall, winds, temperature, and ice across continents and oceans alike. The sky does not ignore the ground. It responds to it, and when continents rise high enough, the atmosphere must learn new rules. Chapter 7. Life Forced to Adapt. Part 1. When continents collide, mountains rise. When mountains rise, climate changes. And when climate changes, life has no choice. It must adapt or disappear. Before the collision, the region between the continents was often a vast ocean or a broad coastal plain. Species lived in connected habitats, spreading gradually across enormous distances. Migration routes were open, ecosystems blended into each other, evolution moved slowly. Geography allowed mixing. But as the ocean closed and the mountains rose, that continuity ended. A barrier formed, not just a line on a map, a wall thousands of kilometers long, cutting habitats into separate worlds. And separation is one of the most powerful forces in evolution. On one side of the rising range, warm, wet air produced dense forests and river valleys. On the other side, dry basins and grasslands spread outward. Animals that once shared territory found themselves isolated. Populations split. A species living across the region suddenly became two populations living in different climates. At first, they were identical, but environments do not stay neutral. In the wet forests, individuals with traits suited for humidity survived better, thicker vegetation tolerance, climbing ability, camouflage among leaves. In the dry lands, survival favored endurance, water conservation, and efficient heat regulation. Generation after generation, small differences accumulated, not dramatically, not visibly, but relentlessly. After thousands of generations, the two populations could no longer interbreed successfully, even if they met again. A single species had become two. The mountains had created biodiversity. Rivers born from high elevations also reshaped ecosystems. Fast-flowing, cold streams carried oxygen-rich water into valleys, allowing aquatic species to diversify. Some fish adapted to swift currents, others to still pools. Insects, specialized for life in glacial meltwater, appeared species that could never exist in warmer lowland rivers. Every altitude became its own habitat layer, from tropical foothills to temperate slopes, to alpine tundra, to frozen peaks. Life stacked vertically. A traveler moving upward would cross climate zones equivalent to traveling thousands of kilometers toward the poles. The mountain compressed planetary diversity into one location. Meanwhile, the disappearance of the ocean eliminated marine ecosystems entirely in the collision zone. Coral reefs vanished as seafloor rose above water. Deep marine organisms lost habitat permanently. Many species went extinct because their environment physically ceased to exist. But extinction always opens opportunity. Coastal animals adapted to inland conditions. Some marine species evolved into freshwater relatives as trapped basins became lakes. Shell-bearing organisms became part of mountain rock, preserving their forms as fossils high above sea level. The past life of the ocean became future evidence. The mountains also redirected migration routes across continents. Animals traveling seasonally now encountered a barrier too high to cross. They were forced to move around the range, sometimes thousands of kilometers farther than before. Over time, entirely new migration patterns formed, some species settling permanently in areas they previously only passed through. Others disappeared entirely, unable to adjust. Geography determined survival more than competition. Plants responded as dramatically as animals. Wind patterns changed where seeds could travel. Moisture differences selected different leaf shapes, root depths, and growth cycles. On wet slopes, towering forests developed. On dry sides, grasses and shrubs dominated. Even soil chemistry changed because erosion from high mountains delivered minerals unevenly across the land. Different plants reshaped the atmosphere locally, altering oxygen and carbon dioxide cycles within ecosystems. The mountains engineered habitats indirectly through weather. High altitude introduced an entirely new challenge: thin air. Animals living near peaks faced reduced oxygen levels. Only those with efficient respiration survived. Over time, lungs enlarged, blood chemistry changed, and metabolic rates adjusted. Some species evolved specialized hemoglobin, able to capture oxygen more effectively. Life learned to breathe differently. Isolation, climate, and altitude combined to produce rapid evolutionary experimentation. Mountain belts became hotspots of new species formation. Valleys separated populations repeatedly as glaciers advanced and retreated, creating cycles of connection and separation. Each cycle accelerated divergence. The mountains did not just host life, they generated it, but adaptation is not universal. Many organisms fail to keep pace with environmental change. Rapid uplift and climate shifts can outstrip evolutionary speed. Fossil records in ancient collision zones show waves of extinction, followed by diversification loss, followed by renewal. Nature restructures itself after upheaval. The collision becomes a reset button, and over millions of years, entirely new ecosystems dominate landscapes that once held oceans. Fish replaced by mammals, coral replaced by forests, marine sediment replaced by soil. The planet moves forward, carrying fragments of its past within new life forms. Because every organism living there now is a descendant of survivors, those that managed to adjust to rising land and changing sky. The continents met, the climate changed, and life reinvented itself. As the mountains continued rising, life did not merely split into two sides, it reorganized across an entire continent. Migration has always been one of the main survival strategies of life. Animals follow food, water, and seasonal climate. Plants spread where conditions allow their seeds to grow. Before the collision, many of these movements happened across open terrain or along coastlines. But now, a barrier stood in the way, not a fence, a planetary wall. For some species, crossing became impossible. For others, only narrow passes allowed movement, fragile corridors where ecosystems from different worlds met briefly. These mountain passes became evolutionary crossroads where species competed, hybridized, or replaced one another. Over time, each side developed distinct biological identities. Two neighboring regions could share ancestry, yet look entirely unrelated after millions of years apart. Large animals were especially affected. Herds that once roamed widely now faced terrain too steep and cold to traverse. Populations fragmented into smaller groups, isolated in separate valleys. Genetic variation accumulated faster in isolation, accelerating evolution. Some grew larger to conserve heat in cold climates. Others shrank to survive scarce resources at altitude. Coat thickness, limb length, and metabolism all shifted according to elevation and temperature. The mountains created natural laboratories of adaptation. Meanwhile, predators evolved alongside prey. New hunting strategies appeared: ambush from rocky cover, endurance pursuit across thin air plateaus, or seasonal descent following migrating animals. Predator-prey relationships diversified, producing ecosystems far more complex than before the collision. Food webs multiplied vertically. A forest at the base of the mountain might host completely different predators than the alpine meadows above it, even though separated by only a few kilometers. Plants also diversified rapidly. Because altitude changes temperature and rainfall over short distances, seeds carried uphill encountered entirely different growing conditions within a few generations. Some species evolved dwarf forms in high winds. Others developed deep roots in dry rain shadow regions. Flowering cycles adjusted to short summers or constant moisture. Entire plant communities emerged unique to narrow elevation bands. In time, the mountain belt became a patchwork of microclimates, each supporting its own biological community. Glacial cycles intensified the process. During colder global periods, ice advanced down valleys, forcing species to retreat to lower altitudes or warmer refuges. During warmer periods, they expanded upward again. Each cycle separated and reunited populations repeatedly. Every separation introduced genetic change. Every reunion reshuffled it. This rhythm dramatically accelerated speciation. Many modern biodiversity hotspots owe their richness to repeated mountain glaciations acting over millions of years. Meanwhile, the disappearance of the ocean left marine organisms stranded in isolated basins. Some adapted to freshwater conditions, becoming entirely new species unrelated to their ocean ancestors, except in deep genetics. Others vanished when salinity changed too quickly. Salt flats and inland seas became temporary habitats for specialized life organisms capable of surviving extreme conditions created by evaporation and mineral concentration. The aftermath of ocean death continued shaping biology long after the water was gone. Birds, capable of flight, responded differently. Instead of strict isolation, mountains created altitude migration. Some species nested at high elevation during summer, but descended in winter. This vertical migration allowed interaction between ecosystems without permanent mixing. Bird populations diverged more slowly, but developed remarkable adaptations to thin air, stronger flight muscles, efficient lungs, and specialized hemoglobin chemistry. They became messengers between ecological worlds. Over millions of years, these processes produced a continent whose biodiversity depended on the mountain's existence. Remove the range, and entire ecosystems would vanish. Life had woven itself into the geology, but evolution never stops. Even as the mountains eventually begin eroding, the species they created remain now adapted to conditions that may slowly change again. Some follow shifting climates upward or downward, others go extinct as their niche disappears. The collision's biological legacy continues long after its geological violence fades. The mountains did not simply separate life, they multiplied it. Where once a single ecosystem spread across open land, now hundreds exist, layered across altitude, climate, and isolation. The impact of continents meeting echoes not just in rock, but in every living organism that occupies the transformed world. By now, tens of millions of years have passed since the continents collided. The mountains no longer feel new. To the life living around them, they have always existed. No creature remembers the ocean that once separated these lands. No forest recalls the plains that stood here before uplift. The barrier is no longer an event, it is part of the natural order. And that is the final stage of adaptation. When change becomes normal, ecosystems stabilize around the geography. Predators and prey settle into long-term balance. Plants evolve to match consistent rainfall patterns, Rivers establish permanent courses through valleys carved long ago by glaciers and earthquakes. Life stops reacting to the mountains. It begins depending on them. Entire evolutionary lineages now exist only because the range divides climate and habitat. Species confined to high altitude cannot survive in lowlands. Desert-adapted organisms cannot cross the wet slopes. Forest species never reach the dry side. The mountains have become a biological boundary as real as an ocean once was. Two continents that physically merged remain biologically distinct. The barrier moved from water to rock over immense spans of time. Even soil reflects the collision. Minerals eroded from the peaks enrich distant plains, allowing complex plant communities to flourish. These plants support herbivores, which support predators, forming intricate ecological pyramids. The fertility of entire regions traces back to crushed rock produced during uplift. Mountains feed life far away from themselves. Without erosion, nutrients would remain locked in stone. With it, they spread across continents. The collision fertilizes the future. Yet the same mountains also limit life. Extreme altitude prevents most species from crossing. Thin air, cold temperatures, and steep terrain form nearly impassable conditions. For millions of years, populations evolve independently on either side. Eventually, they become so different that even if the barrier disappears, reunion is impossible. Geography has permanently altered evolution's path. Time continues. Erosion slowly lowers the peaks. Glaciers retreat. Valleys widen. After perhaps 150 million years, the once massive range may become a chain of gentle highlands. At last, crossing becomes possible again. Animals migrate across areas that were once impassable, but they are no longer the same species that lived before the collision. The biological separation lasted too long. The reunion produces competition, not restoration. Extinction follows again, not from environmental change this time, but from ecological replacement. More adaptable species spread widely, while specialized mountain forms disappear. The final echo of collision reshapes life once more. Fossils buried in the rocks record the entire sequence. Marine creatures from the vanished ocean, early land animals adapting to uplift, high-altitude specialists, and later lowland replacements. A layered archive of evolution responding to geology. Anyone reading these rocks could reconstruct the story: continents meeting, climates shifting, species emerging and vanishing in response. Life becomes a chronicle of moving stone. Eventually, future tectonic events begin elsewhere on the planet. New mountains rise far away. Climate shifts again globally. The descendants of species formed here may migrate outward, carrying adaptations born in the ancient collision. Traits evolved in one mountain range spread to shape ecosystems across other continents millions of years later. The impact multiplies across time, so the biological consequence of continents crashing together is not limited to one region or one era. It echoes forward. From isolation comes diversity. From diversity comes resilience. From resilience comes expansion. Life uses geological upheaval as opportunity. The mountains forced adaptation, and adaptation created new worlds. Long after the peaks themselves fade into low hills, the organisms they shaped continue living unaware that their existence traces back to a slow collision that began before their ancestors even existed. Stone changed air. Air changed climate. Climate changed life. And life never returned to what it was before. The collision is over. The mountains stand high. Rivers have found their paths. Climates have stabilized. And life has adapted to the new world. It feels permanent, but permanence does not exist on Earth, because the same forces that pushed the continents together never stop moving. Deep beneath the crust, the mantle continues to flow slowly, carrying heat outward from the planet's core. The continent's enormous rafts of rock ride these currents, whether mountains exist or not. The collision was not the end of motion. It was one step in a cycle. For hundreds of millions of years before the impact, the continents had drifted apart from an earlier supercontinent. Oceans opened between them, new crust formed, and seas widened. Now they have reunited, and eventually they will separate again. But before separation comes consolidation. After multiple continental collisions occur across the planet, most landmass becomes connected into a single enormous body, a supercontinent. Not just one range, not just one region, but nearly all continents joined into a vast expanse stretching from pole to pole. Earth has experienced this many times. Pangaea was one example, a world where nearly all land touched. Earlier ones existed long before complex life, and future ones will form long after current geography disappears. The present arrangement of continents is temporary. We live in an intermission between supercontinents. As collisions accumulate, oceans shrink. Subduction zones consume seafloor faster than new crust forms. Island chains merge with continental margins. Small oceans close entirely. Eventually, only one global ocean remains, surrounding a giant landmass. From space, Earth would appear unbalanced, one hemisphere dominated by water, the other by land. But this new world would not resemble today's Earth, because geography controls climate, and extreme geography produces extreme conditions. The interior of a supercontinent lies far from ocean moisture. Without nearby seas to moderate temperature, inland regions experience enormous seasonal contrasts, scorching summers and freezing winters. Rain rarely reaches the center. Deserts expand across thousands of kilometers. The largest deserts in history form inside supercontinents. Rivers struggle to cross the vast, dry interior. Lakes evaporate quickly. Dust storms circle the globe, carrying fine sediment into the atmosphere and oceans. The climate becomes harsh. Meanwhile, along the edges of the supercontinent, conditions are the opposite. Warm ocean currents strike the coastal margins, bringing intense rainfall. Monsoons strengthen beyond modern intensity because huge land areas heat and cool seasonally, pulling massive volumes of air inland and outward. Coastal zones become storm-dominated environments. Weather extremes intensify everywhere. The mountain chains created during continental assembly grow enormous. Instead of isolated ranges, collisions stack repeatedly as fragments converge from different directions. Some mountains may stretch across entire hemispheres, the combined remains of many collisions layered over hundreds of millions of years. Earth develops megamountains. Their elevation alters atmospheric circulation globally, influencing temperature gradients between equator and poles. Ice sheets may grow larger because moisture patterns shift dramatically. The climate system enters a new regime. Life faces another transformation. Species, adapted to smaller continents, must adjust to vast interiors and extreme climates. Migration distances increase, isolation zones expand. Evolution accelerates again not because of a single collision, but because the entire planet's geography reorganizes at once. Some species thrive in new deserts and monsoon belts. Others vanish when their habitats disappear completely. The supercontinent becomes both a cradle and a filter of life. Yet even this world cannot last. Heat trapped beneath the giant landmass builds gradually. The mantle beneath it warms because thick continental crust insulates it from cooling. Over tens of millions of years, pressure accumulates below. The same forces that assembled the supercontinent prepare to tear it apart. The cycle begins again. The continents collided to create mountains. Mountains helped create climates. Climates reshaped life. And now the united land prepares for its next transformation. Because Earth does not remain assembled forever. For millions of years, the supercontinent endures. Its deserts expand and contract with seasons, its monsoons roar across coasts, and its massive mountain chains weather slowly under wind and ice. Life adjusts to this extreme world. Organisms evolve to survive long droughts, violent storms, and vast migrations across land that seems endless. From the surface, it appears stable, but deep below, instability grows. The mantle beneath the supercontinent cannot release heat efficiently. Normally, oceanic crust helps cool Earth's interior because it forms and sinks continuously, carrying heat downward through subduction. But a supercontinent covers much of the planet with thick insulating rock. Heat accumulates beneath it like steam beneath a sealed lid. The crust begins to dome upward. At first, the change is subtle, slight elevation across enormous regions. Rivers alter course. Shallow inland seas appear in low areas as the land warps. Volcanic activity increases far from any plate boundary. The interior warms from below. Eventually, cracks appear. Not earthquakes yet, fractures. The crust stretches because heated rock expands. Long rift valleys open across the continent, sometimes thousands of kilometers long. Magma rises into these fractures, forming chains of volcanoes that split the land. The supercontinent begins breaking apart. Where rock pulls away from itself, molten material fills the gap and solidifies into new oceanic crust. A narrow sea forms, growing wider year by year. A new ocean is born. This process reverses the earlier collision. Instead of continents meeting, they now drift apart. The mountains formed during assembly slowly erode while new coastlines develop along the rifts. Marine ecosystems spread into newly created basins. Climate moderates as water invades previously dry interiors. Rainfall returns to lands that were once desert. The planet cools slightly because fresh ocean crust allows heat to escape more efficiently again. Over tens of millions of years, the rift expands into a full ocean basin. Separate continents emerge from what was once unified land. Their edges carry scars of earlier collisions, ancient mountain routes, and suture zones now split across different shores. The geography looks entirely different, yet it contains the memory of the supercontinent in its rocks. Life disperses into new habitats. Species isolated in the interior spread toward coasts. Marine organisms recolonize shallow seas. New ecological competition begins. Evolution accelerates once more as environments diversify. The breakup becomes as biologically important as the collision. Eventually, the continents drift far apart. Oceans widen. Climate stabilizes into a gentler pattern. Mountain building slows worldwide as active collisions decrease. For a time, perhaps 100 million years, Earth enters a relatively calm tectonic phase. But motion never stops. Subduction zones form along new ocean edges, beginning the slow destruction of the seafloor again. The cycle restarts invisibly. Ocean crust created, then consumed, then continents drawn together once more. The next collision is already scheduled in geological time. The mountains we imagined at the beginning, born from two continents meeting, will by then be worn down nearly flat. Future observers might walk across their remnants, unaware that towering peaks once stood there. Yet deep underground, the thickened crust still exists, waiting for another convergence. When the continents meet again, those ancient structures will influence how the next mountains form. Earth builds upon its own past. Continents crash together, oceans vanish, mountains rise, climate shifts, life adapts. The world unites, then breaks apart, not once, but endlessly. The surface of Earth is not a static stage, but a repeating story written in stone and time. Every mountain range is a chapter, every earthquake a sentence, every fossil a memory of a previous world. One day, far in the future, new beings, whatever form life takes, may look across unfamiliar landscapes and see oceans where we see land, and land where we see oceans. And somewhere among their mountains will lie rocks formed in our present era, lifted from an ocean floor that exists today. They will be standing on the remains of our world, just as we stand on the remains of worlds before us, because continents never stop traveling. They only pause between collisions, and the next crash has already begun.